Thank you, Chani. Thank you for this kind introduction. In today's session, we will discuss about the ASIC implementation in Cadence environment. How can we implement a application-specific integrated circuit in our Cadence environment? So let's put some line in our outline that I will covering. First one is introduction, then design flow, CAD tool system, Cadence encounter tool, ASIC implementation step in Cadence that consists further steps. Now, first throw some light on history of your integrated circuit. First, in 1951, William Shockley invented and developed first junction transistor. After 1 year later, Jeffrey W. Dahmer published concept of integrated circuit, and in 1958, Kilby invented suggested the concept of integrated circuit. How can we he introduced the concept of integrated circuit that consists of resistor, capacitor, and transistor on single chip that made up of same kind of material. After that, Noyce also credited for the invention of integrated circuit, and he founded Intel Core in 1959 with his Fairchild colleagues. So the importance of integrated circuit come into existence when Dr. Kilby provided Nobel Prize for his invention in the case of integrated circuit. As we all are very much familiar with Moore's law, by the observation of Moore's, he observed that the number of transistors per chip would grow exponentially, means double in every 18 months. In 4004 microprocessor, transistor with the dimension of 10 micrometer was invented. Transistor with dimension 10 micrometer was implemented, but in Pentium 4, the size of transistor converted from 10 micrometer to 130 nanometer. So but it can't go on day by day because size of transistor can't be smaller than your atom size. So in 2014, your Intel Corporation gave the idea that they generated a chip similar in size with the size of your single rice grain size, and they told that in 2014 with 14 nm technology, they reduced the size to 1/8 part of smaller grain rice size. So on the basis of application, development and manufacturing process, and on the basis of behavioral criteria, IC can be classified into different types. On the basis of application, these are of three types. One is your analog IC, second one is your digital IC, and third one is your mixed signal IC. On the basis of number of components, these are classified into small scale integration, large scale integration, very large scale integration, ultra large scale integration. And on the basis of technology used, these are further divided into TTL family, ECL, MOS, and BiCMOS. But generally, in generalized way, IC can be classified into three types. One is your fully custom, second is your semi-custom, and last one is your non-custom. In case of fully custom, all the logic cell you have to customize, and these are intended on the basis of your applications, to which application you want to implement. In the case of semi-custom ASICs, all of the logic cells are pre-designed, but the interconnection for specific functions are done by customizing few mask layers. In case of non-custom ASIC, all the logic cells and interconnections are pre-designed. Chip are even packaged before any specific application, but the switches we connect, we do on and off on the basis of our application which we want to implement. So what are the advantage of very large scale integrated circuit? First one is reduce the size of circuit. Due to very large scale integration circuit, we can uh, able to able to invent our portable size camera, your laptop, and different applicants. So it also reduces the effective cost of device as the size of your device minimized, increase the operating speed of circuit, require less power than discrete component, high reliability, and occupy relatively smaller area. So these are some advantages of very large scale integrated circuit. In very area, VLSI having the very vast area of applications. There are this diagram showing the application of VLSI in different area. First one is in wireless and wireline. Second is electronic design automation. Third is medical electronics. You all are familiar with biosensor chips. Uh, Fourth one is automotive electronics, aerospace, defense, mass and bioelectronics, and consumer electronics. So these are the application arena of your VLSI system. So it having a vast application in every field, almost in every field. Design flow are very important and having the heaviest demand in a for a design engineer, require the closest teamwork between the consumer and provider. Design flow provide the task to be performed to implement a design into an integrated chip. So the following figure shows a simplified design flow that demonstrate the basic design task and process. Design flow places the heaviest demand for a design engineer, and design flow provides the sequence of tasks that to be performed to implement a integrated chip. The following figure shows a simplified design flow that demonstrates the basic design task and process. This is the design flow diagram. First block representing your system specification. What do you mean by system specification? System specification involves the specification of your algorithm that are you going to implement with the mathematical representation. It gives the idea about the number of gate component that are you going to implementing, and also give the idea about input and output, number of bit in them, so that you can determine the type of interfacing that you are going to done into your for your chip. System specification further involve the input and number of bits used, number of clock that are you going to use in your design, and the number and the frequency of clock that you are going to use for your chip implementation. So which determining the speed of your chip, and the specification about the area, whether your chip is portable or miniature type. So, and also the specification, it involves the specification about the power dissipation, means because the portable devices demanding increase the demand of less power. Okay, so second block is your architecture design. In this block, what we do, there are two type of design entry. First one is your schematic, and second one is your HDL, hardware description language entry. Schematic entry, in schematic entry, what we do, we this is a pictorial representation of your circuit. You are taking the cells that making your circuit. You just drag that cells into your schematic sheet and make the connections between them. But schematic is very difficult, become very complex when your circuit is complex or intricate. In that case, your HDL entry is much better as compared to your schematic entry. So if your circuit is complicated, In that case, we switch to our HDL entry. There are two type of HDL files. One is your Verilog file, and second one is your VHDL file. In these files, we just follow the syntax to implement your design for which application you are designing your circuit. So on the basis of that syntax, you do the entry of your design. Okay, so there are two types, schematic entry and HDL entry. There are some error in this case that may be due to, first is your human error because of unconnected nets, and also due to the error in syntax. There may be two type of error, and another one error, you solve the representation of your circuit in erroneous manner. So we prefer HDL entry as compared to schematic entry when your circuit is complex. Third block is your logic and circuit. We check it for functional simulation. Whether your circuit is correct or not, for that we will check the logic by giving the stimulus to your circuit. Stimulus that you generally know on the word test bench. You create a test bench. You can create a test bench by giving by giving 1 or 0 in your waveform viewer window, as you done in your ISC environment. So by giving that stimulus, you get that response, and on the basis of that response, you find the correctness of your circuit. So that is your functional simulation. The fourth one is your physical layout. In this block, what we do the physical implementation of your design. Once you check your circuit for the correctness, then we do the implementation step. In physical layout step, we will do different steps for the partitioning, floor planning, placement, and routing. Partitioning, we subdivide our circuit into sub-circuit and check for the interconnection, and it is the first step to create the large problem, to convert large problem into small problem, so that you can handle easily and it is in a manageable manner. So after partitioning, we will do floor planning. In floor planning, we devise the area, we determine the dimension of your blocks that are using, and the positioning of your IO pads or pins into your chip. This is a roughly estimate of your chip designing, where we put this instance and where we put other instance. And after this, we do the placement. Placement is optimization of floor planning, we can say, is placement. Here we deal with the actual size of your macros and make the interconnection between them. Further, we do the routing. Routing is very necessary to make the interconnection, and the size of your interconnection wire length should be less, so that the effect of your parasitic components such as resistor and capacitance become lesser. So your wire length size should be minimum as possible. There are two type of routing. One is your detailed routing, and second one is your global routing. Global routing we done is a roughly estimate of your interconnection, and detailed routing is a efficient form of routing. How we put efficiently interconnects. If routing fails, then what we do, we change our parallel processing block into serial processing block, because they require less area as compared to parallel processing block. So after physical layout implementation, then we go for timing verification. It's not always possible that your functionally successful design always successful in timing verification, because if once the design fit into the chip, then delay parameter, net delay and gate delay come into existence. So we will check for these delay, whether our design meeting these specification or not. We will check our timing. We will do timing analysis by specifying on the basis of your specified clock frequency. that you specified during your design specification. So timing and power, after this, we will see for the setup and your hold timing whether they meet or not. So there is always a trade-off between your minimization of hardware requirement and also between your minimization and power requirement and timing issue. So after the timing, once our timing verification is done, then we create our mask layer. That created mask layer is sent to our fabrication unit. That mask layer, we always say that tape out for fabrication. Why we call it tape out? Because in early days, what we do, we send the specification of your mask layer onto the magnetic tape. That's why we are saying tape out for fabrication. But now this time we will send this specification in electronic form. Means you have always heard about GDSII format. So these are the format and which are binary in format. So once your mask layer is created, then that specification we will give to the fabrication unit, and they fabricate your IC. So how are we implement all these implementation? We always use computer aided design tool. What's the importance of these CAD tool? There are different type of CAD tool, as you heard about Centaurus, Cadence. So these are computer aided design tools that assist engineer architect uh, to design the design activity in efficient way. So CAD is used throughout the engineering process, from conceptual design to layout, throughout designing method to the detailed engineering and analysis of component. We use the CAD system. So CAD tools simulate the performance before fabrication. So it save our cost, also resources. So it beneficial in term of time and resources utilization. So CAD tool explore various alternatives and characterize them in terms of cost and performance. Check against all possible non-fabrication process violation before data is given to manufacturing unit. Because we will check before fabrication DRC violation, whether there is DRC violation is present or not. So these type of violation we can check former to the manufacturing before the manufacturing of our IC. So it is impossible today to design an IC without using a CAD tool. So CAD tool having a great importance in case of these VLSI design system. As our session is mainly concerned to much concerned to Cadence environment. So in Cadence environment, we use the tool encounter for the physical implementation of your IC. So encounter tool, first we give the RTL or netlist, gate level netlist to the Cadence environment, and in encounter tool there are 8 steps which it includes. First one is your global synthesis test. After that we will do floor planning, partitioning, time budgeting, then power planning, IR drop analysis. After that, global physical synthesis including detail placement. Then we proceed to hierarchical clock tree synthesis. First we check simulation before inclusion of clock tree synthesis, and after inclusion of this clock tree synthesis, we check for the we check simulation. Then we go for nanometer routing and further RC extraction and delay calculation, and then timing and signal integrity, and ultimately we will get GDSII format file. So now I am discussing ASIC implementation steps in Cadence. As we have done our implementation by using HDL file, that is Verilog file. So first step is that how we share our file from our real environment to virtual environment, right? So there are some steps that you have to follow for sharing of these files to your Cadence environment. Then first step is make a folder in Drive where the CAD image is copied. Okay, you have generated a folder of your name, then paste your file in that folder. Now click at this icon VMware Workstation that will be on your desktop. After that, click at the VM. I will show you. This is your VMware Workstation window. In that, we will go for this VM. Okay. In this VM, we will further go for setting. After going to settings, another window will open, that is your virtual machine settings. In virtual machine setting window, we will go to the options that is shown in your menu bar option. Then we select the share folder. We enabled it by performing this step 7. Click at this always enable icon. Okay. Then now with this add button, click at this add button in this window virtual machine setting. Then add share folder wizard will open. You will have to click at this next button. After it, we browse the folder that have created into our CAD image file, right? After browsing, we will select our folder. Here that folder is CAD. Okay. Then click at this OK and click at this next button. After this, your folder has been shared now. The second step is to enter into virtual environment is go to the option power on this virtual machine. In that button would be shown into your VMware Workstation window. By clicking at this button, another window will open where you have to give the username that is provided by different vendor in different institution. But our username is root, ROOT, and password is root123. When we enter this password, another window will open. Here, there would be a computer icon. Okay, there would be icon for computer. We will double click on this computer icon and we further proceed to different folder that is showing here. Once we go this file system folder, then we go to this mount folder, then HDFS. Here we found that the folder we have shared. Okay, then we will open that folder, CAD folder, then copy these file from that folder, and now again come to back to this window. Here you can see there is ASIC folder which having the name ASIC. Then we double click this folder and here there are some another folder. There is you will find there is counter design folder in which we further go to this RTL and paste our files in this RTL folder. Okay, then we will close this window. Then we will go for this synthesis simulation. For that, we right click on this ASIC folder and go to the option open in terminal. Then a new command window will open in which you have given commands. One is your CSH. Then second command you will have to give source space /CAD /CSH/RC. After that, a new window will open and you will have to type nc launch -new. This is command to open your nc launch tool where we see the pre-synthesis simulation. So which open up the nc launch window. In that, click multiple step create cds.lib file and save it. After saving this, new cds.lib file window will open again, which will have to select the third option, don't include any library. As we are using Verilog file, so for Verilog design, we have to select this option, don't include any library, as pasted HDL files are Verilog files. So this type of window will open, your NC launch window, in which you will have to go for this multiple step, then go for this create cds.lib file. You will click at this button and then we will save it and we will select this third option, don't include any library. Then we press OK. After this, a graphical user interface main window of NC launch is opened. The main window is composed of these three bars. One is your menu bar, file browser, library browser, and console window. Menu bar for fast action, okay, and toolbar for the these are for fast processing of your simulation. And file browser consists the name of files that it consists, and library browser consists the files that it consists of. And console window display the output that you are going to perform, whether there is any error or not. So console window will show the output, display the output of your processing. In this window, you can see here there is RTL folder. We will click at this plus button, which further open this two file lpf.v, lpf_tb.v. lpf.v is your Verilog file and lpf_tb is your test bench, that is stimulus for your system. Okay, so first we select this lpf.v file and then we compile it. We compile it by clicking at this compilation button that is shown here. Once we compile it, then we again select this lpf_tb.v file and compile it. Again click at this compilation button. The result of compilation appear in console window. Once you have done the compilation, then we elaborate our design. To elaborate the design, in right pane you can say that you can see there are two files, lpf and lpf_tb. Then we elaborate one by one these two files. First we select lpf and click at this elaborating button, and again we select lpf_tb and elaborate the button. After elaborating, in snapshot folder, there would be two files, worklib.lpf module and worklib_lpf_tb module. In this folder, we will select the last one, that is your worklib_lpf_tb module only, and we will click on this simulation button. When we click at this simulation button, this type of window will appear. In design browser pane, we double click at this lpf_tb and click on this waveform viewer button window on the navigator toolbar present in upper right corner. It will open the waveform viewer window with all the selected signal displayed as shown in figure 1.9. This is your pre-synthesis simulation. We will click at this run button, then we get this type of image on your desktop. Once you have performed the pre-synthesis, we will close all these windows. Then, as we have pasted our file in our counter design folder, then we again go to this counter design folder, and in counter design folder we go to this synthesis folder. In synthesis folder there are many type of files, but we have to concern only about the rc_script.tcl file. rc_script.tcl file, we display it Okay, as our name of our filter file is LPF, we will display this file. It would be shown in this manner. Okay, in this file, as our name of file is LPF, so we have to replace this filter with our LPF. So by pressing the key Control plus H, we get a window in which we can replace this filter with your name of filter LPF. Then replace all these filter with LPF and save this file. Okay. As you know that if the order of your filter is much higher, in that case we have to increase the timing, constraint timing. For that we have to open the constraint file that is present in our synthesis folder. So by increasing the time period, we can increase the clock time period, so that if your instance is much greater than, then you have to increase the timing in your constraint constraint file. Sorry. So this file contains period which can be edited or adjusted according to the number of instances in your file. So now again right click on synthesis folder and select open in terminal, which will open the command window. Again we have to type these command. One is your CSH and second one is your source space /cat /CSHRC. To open the required tool type, as we have to perform the gate level netlist synthesis, we open the tool RC in this window and press enter. After some time, RC // will appear on your screen. From here, you have to write some extension, that is source space RC underscore script dot TCL, and press enter. A new RTL compiler window will open. When you type RC, this type of file will appear on your desktop and you will have to give the extension RC source space RC underscore script dot TCL. Then this type of window will open. It generate your gate level netlist. Okay. So when we click at this LPR, double click at this LPR, it will give the hierarchical view of your gate level netlist. By clicking at this zoom in and zoom out, we can view the instances present in our filter design, in filter gate level netlist. Once we have created gate level netlist, then we close all the window and then we go for this physical design implementation step. For physical design implementation, this physical design folder present again in counter design folder, we will right click on this and go to the option open in terminal. Write a command, again CSH source space /cat /CSHRC. Now we open the encounter tool, because for physical design implementation tool is encounter. So we will have to write encounter into our window to import the physical design by typing the command encounter and press enter. So a new window RTL2 GDSII system window will open. In this we will go for file. In your menu bar, you can see in this window there is file at very first position in left hand side. We will click at this file and we will go for this import design. When we click at this import design window, this design import window will open. So to add the files, we will go for this button, this triple dot button. When we click at this button, a new window netlist file will open. In this, we will go for this button. We will click at this button, and after that, A new window, Netlist selection will open. In that, we go for this up folder button. We will click at this, and when we find when we find synthesis folder, then we double click at the synthesis folder and select the file filter underscore netlist.v and add it by clicking at this add button present in this window. Now we will close this window. In design import window, again we will select this left file, LEF files. Again we will go for these triple dot, and when we go for these triple dot, we will select from left folder these last two files, gcslib 090 underscore translated dot left file. Okay, so these two files we will select and add them, and we will close this window. In design import window, again to add the power nets we will give the name VDD, and for ground net we will give the name VSS. And then we click at this create analysis configuration button. When we click at this create analysis button, the triple MC browser window will open, in which we will have to give in the library sets. Library sets, we will double click at this library sets and add this window will open timing library file, in which we further go for this folder option, and from library we will select for maximum timing we will select slow.lib file, and for minimum timing we will select this fast.lib file. Then again we go for this triple MC browser window, in which we will go for delay corners. Double click at this delay corner. Now first we write the name of delay corner is minimum delay. Okay. When we click at this delay corner, this add delay corner window will open, in which we will give it name max underscore delay, for which we will select an attribute from library set max underscore timing. After selecting this, we click at this OK button. Again, we will double click at this delay corner, and now we will name it as minimum underscore delay. Okay, and for that we will select from library set minimum timing. Again we press OK. After that we add the constraints. Okay, when we click at this double click at this constraint, this add constraint mode window will open, in which we will give it to name, we will give its name constraint, and in SDC constraint file we go to this add button. When we click at this add button, SDC constraint file will open, and again we go for synthesis folder and double click at that synthesis folder and select these files with extension .sdc. And again we click at this add button and close this window. After that, again we go for this triple MC browser window. Now we will double click at this analysis view and named it as worst. Okay, I will show you. This window will open, add analysis view. In this window, for delay corner, we will select the option max underscore delay, because if your delay is maximum, then analysis view is worst. Okay, again we will double click at this analysis view in MMC browser window. Now we named it as best for minimum delay. Here in delay corner, we select minimum underscore delay and we press OK. After that, for setup analysis, We double click at this setup analysis in MMC browser window. Then this window add setup analysis view window will open. In that, for we will select this worst and press OK. After that, for hold analysis, we double click at that hold analysis in MMC browser window, and we select this best analysis view is best and press OK. Once you have done Once we have done it, we click at this save and close button in MMC browser window, and after that we will click at this save button that present in design import window. Okay, when we click at this save and close button in MMC browser window, a window will open. You have to save the name of file with extension .view. Okay, but when we save the files, the press the button save that present in your design import window, then again you have to save the file, but in that case extension would be .globals. These two type of window will open when we click at this save and close button and save button that present in design import window. Okay, as my filter name is LPF, so I have saved this with lpf.view. Okay, and lpf.globals. Once we perform these steps, then we press F. Okay, this type of scenario will be open in your GDS RTL to GDS II system window. After it, we will go for floor planning. For floor planning, we go for the option floor plan that present in menu bar of RTL to GDS II system window, and in floor plan, we go for this specify floor plan. When we click at this specify floor plan, a window will open that which named is specify floor plan. Here we will enter the design dimension, that is your ratio, core utilization, core to left, core to top, core to right, and core to bottom. So in this manner, we will give the inputs in our design dimension system, and we will click at this OK button. Once we have done this floor planning, we will go for this power planning. In power planning, once we add the rings, okay, in power planning, what we do, we add rings or we add strips. Your rings in outside your core area, and power strips within your core area. So we go for this power option, then go to this power planning and add rings. Click at this add rings. Then when we click at this add rings window will open. Then here we have to select the nets. Okay. In design design import window, there are two type of net that we specify. One is your VDD and one is your VSS. Okay, so in that case we have to select the four nets. Net selection window will open. We will select both the nets from possible net. Figure we will show. This net selection window will open. We will select both these VDD and VSS and add them. And we will press this OK. So when we press OK, this nets in add rings window will show VDD and VSS is already selected. After that, in ring type, we select this around core boundary and we select the layer in ring configuration, which matter layer we are going to use. Width of these ring and spacing between these rings. Offset you can center in channel, and you can specify also, and press OK button. So once you press OK, means your rings get added into your physical design. After it, we will select for this add strips. Again, go for this power planning, and then go to the option add strips. In add strips, again we follow the same procedure to select the nets, VDD and VSS, and we select the layer, metal layer, width, spacing between these, and number of sets if you want to give, and stripe boundary, first slice stripe, and then press OK. So once you have done your power planning, then we go for this routing and placement procedure. For routing, again in the RTL to GDS II system window, there is route in menu bar. You click at that route, then go for this spatial route. When you go for this spatial route, a spatial route window will open. You have to select the nets in the same manner as we done earlier and click OK. Now we go for the placement. Click at this place that present in your RTL to GDS II window and go for the place standard cells option. When you go for this place standard cell option, place window get open, and here you have to select run full placement. There are different options. Run incremental placement, run placement in floor plan mode, but we will select run full placement. Then we press OK. Once your placement is done, then we click the button. This is physical viewer button that present in your RTL to GDS II window in right corner. So now this is the visual representation of your ASICs, right? Now there is no any consideration of parasitic component. To see the effect of these parasitic component, that is resistance and capacitance, we go for another option. First we check the timings. First we check for timings. Click at timing that present in menu bar of the same window. Go for this report timing. Timing analysis window gets open and we select pre-CTS because we didn't give any clock tree synthesis. Okay, so first we select this pre-CTS option in design stage and set up in analysis type, and we will click at OK. Now we will see the timing report that would be shown into your console window. Here you will see if the timing is negative, okay, then you go for optimization step. You will have to go for optimization step. Timing always should be in either 0 or positive. There should be no negative value. So to optimize that design, we click at this optimize button. Then go for this optimize design. In optimization window, an optimization window will open. In optimization window, we will select pre-CTS and click OK. And again, we will check for timing report. You will see here if it's 0 or positive value, then proceed. Let's again check for timing. This is your optimization window in which we will have to select this pre-CTS option and we will click OK. And this is your timing report. Here you can see the timings are 0, so means it's OK. Then after that, we synthesize clock tree. To synthesize clock tree, we go for this synthesize clock tree option in RTL to GDS II system window. And we will click the button. We will click the button generate clock specification in synthesize clock tree and select all the clocks. We will select only the clocks in generate clock specification window and click the button add to add the clocks in selected cells. Now your clock tree synthesis has been done. Now once again we will check for timing, but now we will select post CTS option because your clock tree synthesis has been done. So we will select post CTS and again we will check for timing. Then after checking the timing, this is your window that would be generate synthesize clock tree. In this we will go for this generate specific button. Then this generate clock specification window will open and here we will select clock only and add them into the selected cells. After that we will go for this route. Again we will do routing because in this time we are doing detailed routing. So finalized. So go to this route, nano route, and then again there is again route option. Nano route window will open. Then we will select in nano route window. We will select in this manner all the specification, that it is routing phase, concurrent routing features, and we will click at this OK button. After this, we consider the effect of parasitic component. To see the effect of these parasitic component, we click at this timing and then go to the option extract RC. Okay, and select all the option in extract RC window and click OK. Again click timing and then go to the option write SDF and we will calculate delay window. Calculate delay window gets open. We will select here lpf.sdf file. Okay, and click OK. After all this procedure, we again click the file option that present in menu bar and go to the save netlist. Save netlist window will open and we will select lpf.v file with .v extension for netlist file and we will click at this OK button. Once we have done our physical design implementation, then we again double click at this ASIC folder and go to this counter design folder. In counter design folder, we will go to the physical design folder and copy two files of with extension .v and .sdf from the later folder and paste in the simulation folder because now we want to see post synthesis simulation. So for that we have to copy these two files .v and .sdf from later folder, that is your physical design folder, and paste into the simulation folder. Double click this lib folder, again click 90 folder, means because these are showing the technology used. There is 45, 90 and 180 nm in our Cadence environment. I'm using this 90. So that's why we click at this 90 folder and we will copy the slow.lib file from here and paste into this simulation folder. So now check the simulation folder, which consists of these four files: slow.v, lpf.v, lpf_tb.v, and the last one is your lpf.sdc. Display slow.v, lpf.v, and lpf_tb.v file simultaneously, and copy the first line of slow.v file into these two files at first position and save them. When we display this slow.v file, this first line we will have to copy and we have to paste into other two files, and we remember that always save that. For post-synthesis simulation, we will have to click on the simulation folder and select open in terminal, and again we will write command csh source space /cad /cshrc. A new window will open that will open in the case of pre-synthesis